In this video, we're going to continue talking about enolates, and mostly what we're going to talk about is alkylation of enolates. What we've talked about in the previous videos is that we can deprotonate these alpha positions to make them into enolates, to give them a negative charge, and that those can react with electrophiles, but what we've talked about up to this point is other aldehydes, other ketones, other esters, which are pretty good electrophiles, but we've seen better electrophiles, namely alkyl halides, which is what we're going to be talking about in this video. So let's say you have cyclohexanone. What we can do is deprotonate it with under non-equilibrating conditions like LDA. So after step one, what's going to happen is we're going to remove this alpha hydrogen. So LDA is going to remove that. And we're going to get an enolate. Right? We're going to have a negative charge on carbon, which can then react with an alkyl halide. Let's say we used ethyl bromide or something. Well, then this negative charge can attack this carbon and kick out the leaving group. Remember, this is an SN2 reaction. So our R group here would be an ethyl group in this case. Whatever alkyl halide you want to use, you want to remember the rules for SN2 reactions. It needs to be non-hindered, good leaving groups, things like that. Mostly primary alkyl halides are going to be the best for these kinds of reactions. So that's alkylation of ketones and aldehydes and esters. If you have a single carbonyl, that's pretty much what you're going to see. That's a pretty straightforward reaction. You generate your nucleophile and then you use it in an SN2 reaction like we've seen in the past. Pretty straightforward. What we're going to spend the rest of the video talking about is somewhat more complicated reactions, but we can understand these based on pretty much what we've already learned. So this reaction shown here is a three-step procedure called the Malonic ester synthesis. So the Malonic ester synthesis, you start with a diester. So this is called diethyl malonate. It has two ester groups. We can deprotonate it with a base to form an enolate, right? And then that enolate can react with an alkyl halide. In this case, we reacted it with benzyl bromide. So this carbon right here is our electrophile. This carbon, once we deprotonate it in step one, is our nucleophile. So we attack this carbon and we kick that out. So after step two, what we're going to have is the alkylated product of our enolate. So we did the first two steps are just an enolate alkylation. And that's going to be the product after step one and two. But step three is interesting because remember, strong acid and heat, or aqueous acid and heat, will convert both of our esters into carboxylic acids. That's called acid catalyzed hydrolysis of an ester. So we get a carboxylic acid here, and we'll get a carboxylic acid here, but then we can get rid of one of these carboxylic acids through a process called decarboxylation. So the final product is going to have an OH here, and it's going to have 1, 2, 3 carbons, which are these 1, 2, 3 carbons, and we spit out carbon dioxide as a byproduct of the reaction, as I'll show you on the next slide. Okay, so let's talk more about this step 3, this decarboxylation step, because this is the most mysterious part about the malonic ester synthesis. So let's say remember we started with diethyl malonate, or you can also use dimethyl malonate. Any kind of diester will work for this. We deprotonated it with a base, so then we got our enolate. We reacted it with an electrophile. I'm just going to abbreviate the aromatic ring with a pH here. So that lone pair of electrons attacked the carbon. We kicked out our leaving group, so we had our alkylated diethyl malonate. Okay, so we're here. This is what we talked about on the last slide. Now, I'm not going to show you the mechanism for the sake of time and space, but we've already talked about it in a previous video. This is acid catalyzed hydrolysis of an ester. We're going to hydrolyze this ester, and we're going to hydrolyze this ester. So we're going to get here So far, so good. Now is when the interesting step happens. We had heat here. If you take a diacid like this, a malonic acid is what this is called, and you heat it, one thing that can happen is this bond can freely rotate, and what we get is a hydrogen bond between this OH group and this carbon-oxygen double bond, which looks kind of like this. You can draw the hydrogen bond as kind of like a dotted line there. And so then this oxygen, what can happen if we heat the reaction is a process called decarboxylation, which means that we lose a molecule of carbon dioxide. Notice that we have an oxygen, carbon, oxygen. So this is what we lose as carbon dioxide, and the way that works is that the lone pair of electrons pulls off this acidic hydrogen. These two electrons become a pi bond to form carbon dioxide. We break this bond to form an enol. And we could either show this lone pair of electrons or probably be better to show the pi bond. So then the result here is that we have carbon dioxide, right? We have carbon-oxygen double bond, carbon, carbon-oxygen double bond. This bond broke, so this carbon isn't bonded to this carbon anymore. These two electrons became the pi bond. These two electrons became a new OH bond. And that's still there. This is an enol, right, which could rapidly tautomerize under the aqueous acidic conditions. So this is a tautomerization to give us our carboxylic acid. So this is a really nice way to make substituted carboxylic acid instead of deprotonating a carboxylic acid, which would be really difficult because you have this acidic hydrogen. We can put on any R group that we want to, right? Notice that this group got tacked on to any carboxylic acid. So we start with an alkyl halide and diethyl malonate, and we end up with an alkylated carboxylic acid. That's the malonic ester synthesis, right? We can even do two alkylations, right? We can deprotonate, add one alkyl halide, deprotonate again, add another alkyl halide, so now we have two R groups, and then acid catalyzed hydrolysis turns these both into carboxylic acids. Decarboxylation cuts off one of our carboxylic acids, and we get our dialkylated carboxylic acid out of the malonic ester synthesis. So we can do that as well if we would like. A related reaction is called the acetoacetic ester synthesis. So instead of starting with a diester, we start with a beta keto ester, right? We can deprotonate that beta keto ester with a base to get an enolate ion, right? The enolate ion can attack our alkyl halide and displace, so we get a lone pair of electrons, we attack here, we kick out the bromide. And so again, after step 2, what we have would be something like this, right? And now when we add acid and water, we hydrolyze the ester. Notice now there's only one ester. So we hydrolyze the ester, we get an OH group. This can undergo decarboxylation to remove carbon dioxide. And so notice that the result is a new alkylated ketone. So in a sense what we've done is we've taken this carbon right here and we've tacked on a CH2 and a ketone and a CH3. So in the previous case we had a carboxylic acid here. In the malonic ester synthesis we get an acid here. In the acetoacetic ester synthesis we get a ketone. So to summarize, we can generate enolates under non-equilibrating conditions with like LDA, and we can react them with electrophiles like alkyl halides to get alkylated enolates. This is a really nice strategy for forming new carbon-carbon bonds. And in more complicated reactions, what we can do is start with malonic esters or with acetoacetic esters. We can easily deprotonate those to make nucleophilic enolates, which can then react with electrophiles. we're always going to deprotonate first, then alkylate, then carry out a hydrolysis reaction, which will simultaneously, which will be followed by a decarboxylation to give different alkylated carboxylic acids. Similarly, we can get alkylated ketones by the acetoacetic ester synthesis. Dialkylation is also possible. Make sure you know the mechanism for all these reactions.